Hello, YouTube, and good evening. This is Drew, and welcome to the very first video of the series, May the Code Force be with you. Um, Basically, in this series, I'll be taking a look at some problems that I've encountered along the way, and I'll try to explain it to the best of my potential, and hopefully we'll all learn something from this process. Today we'll be looking at the recent educational round 180 rated for Division 2, and we're looking specifically at its question D, which is reachability and tree. This is 2025, 1st of July, by the way. In case you're reading this in the future, hello from the distant past, and let's begin. So here we let U and V be two distinct vertices in a directed graph. Let's call the ordered pair UV good if there exists a path from vertex U to vertex V along the edges of the graph. Now the problem gives us an undirected tree. We have n vertices and n-1 edges. The problem asks us to determine whether it is possible to assign a direction to each edge of this tree so that we have exactly n good pairs in it. If it is possible, then we should print the way to direct the edges resulting in n good pairs. For example, in the chart below, we have a tree of 5 vertices and 4 edges. And the solution, given in the blue lines, present 5 good edges, which are respectively 3 to 5, 3 to 1, 1 to 2, 4 to 2, and the last one, 3, 2, because there's a path from 3 to 1 and then to 2. So 5 good pairs in total. Now, before we really start diving into the code, we should start from the basics, like what makes a pair good. First of all, the most basic scenario is that if you have two vertices directly connected by one edge, we call them neighboring vertices, just to be specific. Neighboring vertices, no matter which way you assign the edge between them, you'll always result in one good pair. For example, in this scenario, there is a edge going from U to V, hence the pair UV is a good pair. If we take this edge and we reverse it, then there's also one good pair, which is VU. Notice that this pair is ordered, and order does count in this problem, so it is necessary to keep in mind because later we'll have to use it. 2 nodes, easy, simple, right? What about 3 nodes? Now, 3 nodes, we have 2 scenarios. One is that we have a straight path going from U to V to T. In this case, we have one extra good pair besides the 2 edges. We have U to V, this is one pair, V to T, the second pair, and the third pair, which is U to T, taking V as a median node, and we have a path from U to T. Hence, in this case, we have 3 good pairs. And if I take the edge from V to T and I reverse it, now the number of good pairs is not 3 anymore. It becomes 2 again, because now there's no longer a path from node U to node T. This third good pair no longer exists, and the number of good pairs returns to 2 again, which is U and V and T to V. The question is, how do we generalize? We're looking for an entire tree, and one tree, or specifically one node in a tree, can have many neighbors, 4, 5, you name it. How do I make sure that I can create a directed tree that the n-1 edges can result in n good pairs? So here's the generalization logic. It involves something similar to a combination, but it really is just an extension of the cases that we covered before in the previous slide. So we take any node n in this undirected graph. Let the degree of n be k, which means basically that the neighbors of this node n is exactly k. So we have k neighbors, which means k edges, connecting n with these k neighbors. Now we apply direction to the k edges. and let the number of outgoing edges from n be a, which means there are a edges with n as a starting point and one of the neighbors as an ending point, which means we have k minus a incoming edges, which take n as a destination rather than a starting point. Then we can see that if we choose one of these edges from the outgoing edges and one of the edges from the incoming edges, respectively to node n, we can find that these three nodes and two edges together form the second case in our basic example in the previous slide, right? So this is one of the neighbors, this is node n, and t is the other neighbor. Of course, n is in the middle. We have one going into n and one coming out of n. Right, so here we have, remember here, we have three good pairs because this n, here it is v, it acts as a middle node connecting the two neighbors. Now in this case, we are not exactly restricted to one incoming neighbor and one outgoing neighbor. We have a outgoing neighbors and k minus a incoming neighbors. Any one of which from these two sets can form a three-node line in which we have one extra pair of good nodes, which means altogether, if the number of outgoing edges from n is a, then we have the number of good pairs between n and its k neighbors is k, because we have k pairs of directly connected vertices, and any direct pair of directly connected vertices will result in a good pair. So we have k as the basic, plus we have a times k minus a, which is the n as a middle node scenario covered in the previous slide, which means now we can take a look at the question itself now that we have some logic of what is going on. So, okay, back to the question. We have n nodes, n minus y edges, and asks for n good pairs. So we need exactly one extra pair of good nodes. How can we manipulate the k and a? We can play around with these values a bit. See how they can yield us one extra good pair. So actually the answer is simple. We take k equals 2 and a equals to 1, which is, interesting enough, this case. The second case that we've covered so much, but now I'm going to refer to it again because this is the crucial part in determining whether the tree is possible to yield n good pairs rather than, let's say, n plus 1, n plus 2, or some other amount of good pairs. The deterministic requirement for n good pairs is that in this tree, we must have one node of degree 2, which means we have two neighbors, and applying the previous scenario gives us one extra pair, and that is all we need to create n good pairs because n minus 1 edges implies n minus 1 pairs of good nodes. And if we have, right now, we have n good pairs because we have a degree 2 node, we have one incoming edge, one outgoing edge, and the extra pair of good nodes provided by the path from the one neighbor to the middle node 2 to the other neighbor. Now we just have to ensure that no other three node pairs, the node triplets, let's call them triplets, can be formed in all these other nodes and their neighbors. So the way we process this is we forcefully make a equals to 0, which means that we have no extra good pairs between any node n and its neighbors, because when a equals 0, we have no extra good pairs. So besides from the special degree 2 node that we need for the one extra edge, the other nodes should be purely outgoing nodes or incoming nodes. That way we can ensure that there are no extra pairs generated in the process of assigning directions to all these edges. So we have a starting node, we have rules to guide us, then the formulation of the direction of the tree can be implemented using breadth first search, and it is roughly implemented in O(n) time. So we can take a look at the code. Here we initialize two vectors. One is actually a matrix where we record all the neighbors for each given node, and one is to record the degrees of the nodes. We initialize the tree, and for each undirected edge we read, we push the neighbors into their respective locations, and we add 1 to the degrees of the two nodes respectively. Then we first define whether it is possible to reach the n good pairs condition asked by the question. And to do that, we simply iterate through degrees. We iterate through the vector, and we see if there is a node that corresponds to exactly degree 2. If there is one, then we simply take this node, let's say node I, in this case, node I has a degree of 2, then stop. We can take node I as the root node, and everything else starts from root I. And we can break, and we know that it is possible. If not, it comes back to my previous formula of k plus a times k minus a. If we do not have a node of degree 2, what will happen? Well, there are two scenarios basically. One is that we're falling one short. We have n minus 1 good pairs, but we're missing the one extra pair. The other scenario is that we have too much, because any node with degrees of 3 and above, if we ever try to choose to create the node triplet scenario in the previous slide, it will result in more than enough node pairs, because when k is larger than 2, no matter which a you choose, other than 0 and k, will result in a number larger than 1. That's combination. Hence, if we do not have a node of degree 2, we'll simply print no, and the program ends there. If not, we'll go into the breadth first search. Okay, if flag equals to yes, we'll initialize two more vectors to help us record what is going on. One of these is the state vector, which determines the nodes other than the root nodes. What are they? Are they purely incoming nodes, or are they purely outgoing nodes? And of course, we have the classic visited vector recording all of the nodes that we have visited, so we don't have to visit them again for the sake of simplicity. And we'll have a queue. This queue is to record all the nodes we have yet to visit. Of course, starting from the node k, which previously has been assigned to the value of 1, so that this node is the degree 2 node, we first initialize this tree by applying one edge of this node k as an outgoing edge and one edge as an incoming edge. In the picture below, as the previous test case, the special node k is 1 because you see that it has degree of 2. And of course, node 3 has been assigned to be the incoming neighbor, and node 2 the outgoing neighbor. Of course, the states of these two neighbors will be recorded, one to show that it is a purely outgoing node, which in this case corresponds to node 3, and -1 to show that it is purely an incoming node, which corresponds to node 2. And we'll push both these two nodes into the queue because these are not nodes that we have visited yet. After initialization, the root is included in the visited state, and while the queue is not empty, we basically implement breadth first search throughout this graph, and each iteration will take the first element that we're looking, and we iterate through all its neighbors. We'll see if it is not visited. If it is not visited, we assign to it a state. of course, this state will be the inverse of whichever state that the current node you're looking at. Let's say I'm currently standing on a outgoing node. Therefore, all the neighbors of this outgoing node, besides the root node, will be incoming nodes. Therefore, we'll apply the inverse to the neighbors. And of course, when we apply the inverse, we can, at the same time, record the direction of the edges, because we have the state of the current node, we have the state of the neighboring node, which means that the direction of the edge between these two nodes is actually fixed. We cannot change it anymore. So at the same time, when we record the state, we output the edges as required. If it's currently an outgoing node that we're standing on, we take the current node as a departure and the neighboring node as a destination. If not, then the other way around. The neighbor is the departure and our current node is the destination. And then, of course, we'll push all our neighbors that have not been visited into our queue. And at the end of the loop, we have visited all our neighboring nodes and determined every edge corresponding to the current node. So we update its visited state to 1, and throughout this while loop, we'll iterate through all the nodes and all the edges. Besides the initialization, we'll make sure that all the other edges will produce no extra good pairs, which means we have n-1 basic good pairs and the one extra good pair generated by the degree 2 node. And this solution works in roughly ON time. Curious thing about it is that when I try to submit this solution in Python, it gives me a time limit exceeded on test case 12, which I presume has something to do with the way Python and C++ handle lists, which just to show how important it is to use C++ for this problem. But overall, a very math-like combination problem, and is actually very intuitional, which is why I chose this question as the very first video of the series. I'll be posting both the links to the question and the links to my submission below. That's it for today. Thanks for watching. Happy coding. I'll see you next time for the second session of May the Code Force be with you.